In Section 2.1, we're going to be learning about relations and functions, and we're going to focus on how to graph relations and then also how to identify whether something is a function. Let's start with some definitions. First of all, we need to discuss what a relation is. A relation is a set of pairs of input and output values, or we also might think of those as ordered pairs or an x and a y coordinate. There are four common ways which we represent relations. The first way is what we just discussed, and that's as ordered pairs, where you have an input and an output. So we have the ordered pair 2, 5, 7, 3, 1, -2, -2, -2, and 3, 4. Now those can actually be put into what we call a mapping. In a mapping, what we do is we have our input and our output paired together with some arrows. So in our first column, notice that's where you're going to find your input. And that's where we have our ordered pairs. And notice that I've gone ahead and put them in numerical order. So we'd have -2, 1, 2, 3, and 7. Then in the second column, we have our output. And then what we do, and again, I've put those in numerical order. We have -2, 3, 4, and 5. Then what we do is we just connect the pairs with arrows. And you can see that I've connected all of the corresponding inputs with outputs. Another way we might see that same data is in a table of values, sort of like an XY chart that we're used to. So writing them as ordered pairs, but just in a table of values. One last way we may see the same data is to see it in a graph. And notice here that I have plotted my x and y coordinates, and there's my x-axis and my y-axis, and I plotted it like we would normally plot ordered pairs. Now let's focus on some terminology that we're going to use in this section. First, we have the term domain. The domain is our set of inputs or our x-coordinates of our ordered pairs. The range is our set of outputs, and it's the y-coordinates of our ordered pairs. Then a function is a relation. Now remember, a relation is just any ordered pairs, but in a function, each element of the domain corresponds with exactly one element of the range. So going back to our domain and range, remember that if we put these in alphabetical order, they also pair up correspondingly with our x's and our y's. Domain is x, range is y's. Let's take a moment now and apply what we've just looked at. Let's find our domain and our range for each of these relations, and then we're going to determine whether or not this forms a function. So in our first example, let's look at our domain. So our domain is the set of numbers -2, 0, 1, and 3. And our range is our corresponding set of y numbers, which would be -3, 1, 3, and 4. Now notice that I did put those in numerical order. That's normally the way we would write that. Now to determine whether it's a function or not, every element in our domain needs to be paired with exactly one element of our range. So if you look at our very first number in our domain, that actually has been paired with two separate values in our range, so we would say that is not a function. Now in our next example, we've got them listed as ordered pairs. So let's do our domain. And again, let's try to put these in numerical order. So if we go through here, our smallest value of x would be -3. Our next value of x would be 2. And then 5. And then 7 and 8. Now our range would be our y's. So our smallest y value we had was 0, and then 4, and then 7. Now what we want to focus on then is looking back at our ordered pairs. Did we use our x values more than once? and were they paired with a different y value? So we have an x value of 5 that was used twice. And that 5 was paired with two different y values. It was paired with 7 and it was paired with 4. So this would again be not a function. Now, when we have a picture of our graph or our relation, we can use what's known as the vertical line test to test for a function. So what you do with the vertical line test is you want to see if you can find a vertical line that passes through more than one point on the graph. If that happens, it's not a function. So looking at our first example, imagine that vertical line, it touches our graph at only one point. And there's another vertical line that would touch at one point. And every time I draw a vertical line, no matter where I draw it, it's touching my graph at only one point. So we would say that this is a function. Now looking at our next example, there we touch at one point. There we actually touch our graph at 3 different points. So as soon as we find that, we know that this is not a function. Now again, some more terminology that we're going to discuss in this chapter. Let's look at the term function rule. A function rule is an equation that represents an output value in terms of an input value. So this would be an example of a function rule. Y equals 3x minus 2. Y is my output value, and it's based upon my x value. If we have an independent variable, then that would be our inputs. So in our example here, y equals 3x minus 2, our independent variable was our x. Our dependent variable is the outputs, which in our example was our y's. Notice that the y value depends on the value of x. You compute your y when you know what your x value is. Another way that we can represent those is to use something called function notation, and it allows us to represent a function in terms of its independent variable. So instead of saying y equals 3x minus 2, we could say f of x equals 3x minus 2. This is a really important concept, that f of x is the same thing as y equals. So y equals 3x minus 2 is equivalent to f of x equals 3x minus 2, because y and f of x mean the same thing. Now let's use this idea of function notation and compute some output values based on their input values. So taking the function 3x minus 2, how would I compute, or what would I get if I computed for x equals 1? Well, the way I write that is I would say f of 1, because that's my input, would be 3 times 1 minus 2, which would be 1. We could also find what happens when x is negative 3, which we write that f of negative 3. So that would be 3 times negative 3 minus 2. Negative 9 minus 2 would be negative 11. And then f of 2/3 would be 3 times 2/3 minus 2. But 3 times 2/3 would be 2, and 2 minus 2 would be 0. Now let's apply this to a real-world concept. Let's say that we have tickets to a concert are available online for $35 each, plus a shipping fee or handling fee of $2.50. The total cost is a function of the number of tickets that we bought. So what would be a function rule that models the cost of the concert based upon the number of tickets that we're going to buy? And then we're going to evaluate that for 4 tickets. So let's use C to represent the cost, and it's based upon the number of tickets we buy. So we'll call that C of T. And to find the cost, we're going to take $35 times the number of tickets, because they're $35 a piece, plus then we have to pay our handling fee of $2.50. So our equation for our cost based upon the number of tickets would be 35T plus $2.50. Now let's evaluate that for 4 tickets. So if I put in 4, I'd have 35 times 4 plus $2.50. But 35 times 4 would be 140 plus the $2.50. So that's going to give me $142.50 would be our cost based upon the fact that we bought 4 tickets.